phase, and then I've shown it stopping at some value, okay? The quad phase, on the other hand, you remember we showed that there was a zero crossing with the quad phase. What does that mean when we get out and dig a hole in the ground? It means that near the surface, the electric field is in one direction, but all of a sudden it changes sign, and as we go to greater depths, it's in the other direction. That, to quote Alex, is unpleasant behavior. Because we ask ourselves now what's going to happen to this rod as we drop it down into the ground. Why do we do that? We want to know how the measured response will vary with the depth to the rod. And we see that as we drop the rod down, and if we measure only the in-phase component of the secondary magnetic field, that the response will vary quite nicely. As the target goes down deeper, the magnetic field from the now deeper current flow will be less on the surface. So as we drop the target down, the in-phase anomaly will vary generally quite nicely. Geez. Do both projectors do that?
I don't know. Maybe I'll put on the other one.
Might be useful to tell you what we can do. Yeah, well, I'm nearly finished with VLF and we're nearly ready for a break. So. Yeah. Oh yeah, gotcha. Do you want me to flip them through?
That should have been all right. Can you move it forward a bit more?
Yeah. Okay, well let's go back to El Diablo and we can figure out what we're going to do at slide projector 2 is off. Any questions? All very clear? I don't have the nerve to ask you to put your right hand up. Okay, good. I have to go back a bit. That should be. Okay, so as we put the conductive rod, or we know now virtually any target, down deeper and deeper, obviously it's going to be grabbing. If you're, and this will cause Alex a good deal of heartburn when I start talking like this, but as you put the target down, it's going to be grabbing some of the current in this direction and some of the current in that direction. And as you drop it down, the response is going to be a dog's breakfast with depth. And indeed it is. And you'll see that tomorrow. Basically then what we conclude from all of this is that if we're going to do VLF measurements, we have to be prepared for galvanic current component. That's going to dominate the response. The quadrature phase response, and you heard it from somebody that sold the first instrument that measured quadrature phase response, is going to be very difficult to interpret. And my own suggestion is that you, unless you're very gutsy, that you ignore it and you do your interpretations on the in-phase component. Okay, one last bit with VLF and then we'll tidy that one up. Once we understand that there is an electric field in this direction driving currents as shown, and I'm talking here about only the in-phase component, it becomes relatively simple to understand the sort of response that we're going to get from a vertical contact. I divide the Earth into two sections, this one and this one. This one is resistive, this one is conductive. There's a vertical contact between the two of them. What do we know about the current flow in the ground in each region? Well, in the resistive side, we know, as we said earlier, that the skin depth will be large. If the skin depth is large, that means that the currents will go down to quite large depths. On the other hand, on the conductive side, the skin depth is small, and we expect the currents to go down a relatively small depth. The total amount of current is the same in both cases. They're just distributed to greater depths in the more resistive side. We also know that the effect of the contact, very roughly, and we're waving our arms a lot, is going to fall off fairly slowly in this side, because beyond 1 or 2 skin depths, the currents are not going to know about the contact, but the skin depth is large. So we expect the variation of current flow to vary fairly slowly in this material. On the other hand, here the skin depth is small. Same argument says that even when we're fairly close to the contact, the currents will start to reach the equilibrium value far from the contact. If we very roughly apply the Biot-Savart law to these in our mind, to this sort of current distribution, we would guess that very roughly this current flow, when we apply the right-hand rule and estimate what the magnetic field will look like, will probably be tilted as we go across the interface. Tilted, of course, means a vertical field component, and we said earlier that the variations as we go across here will be fairly slow as the large skin depth. So we expect that vertical component to fall off fairly slowly on the resistive side of the contact. On the other hand, on the conductive side, we expect it to fall off more rapidly. And so we wouldn't be surprised if we got an anomaly like that from the contact itself. And indeed, that's exactly what we get. Here's the vertical field component across a contact between 10,000 and 1,000 ohm meters. We see that it peaks right over the contact. It decays fairly slowly. I've sketched in the 2 skin depths for a typical VLF frequency. There's the large skin depth and the 10,000 ohm meter, small skin depth and the 1,000 ohm meter. See it fall off quickly, see it fall off slowly, see in general how we could guess what it's going to look like, and see how ugly the quadrature phase component looks like. Who could predict that that's what would have occurred? Or conversely, who on looking at that would have said, aha, vertical contact? Generally, stick with the in-phase component. Let's have a break.
Quick question.
Yeah.
When I said I understood the quadrature, in the VLF I've done, we've measured tilt angle and direction. To measure quadrature, you have to know the primary phase.
For which we use the horizontal magnetic field. Most VLF systems measure, for example, either tilt angle and ellipticity, or directly the in-phase and the quadrature phase components of the magnetic field. What do they use as their phase reference? The very large horizontal magnetic field. And so we can measure I and Q with respect to that large phase reference. So no problem there. Today for VLF, are there any questions, or were you, I suspect that most of you are not terribly familiar with VLF to start with. It's not necessarily a tool you want to use in Western Australia, I might add, but one of the reasons for discussing the galvanic current component response to VLF is that the same factors apply to other plane wave systems, and that is, for example, audio frequency magnetotellurics, control source audio frequency magnetotellurics, which are used out here and are definitely used in Australia, and also MT itself, okay? And I'll discuss a bit more about that. Okay, so the comments then on the VLF exploration, we saw galvanic currents dominate. They affect the determination of depth, etc., etc. In short, they don't do anything to make the surveys more easily interpreted. They are, nevertheless, still in resistive ground, a reasonably useful technique for rapidly mapping geology. Next then, MT, AMT, and CSAMT soundings. Now we're going to measure E and H. And now I want y'all to unhook the right arms. How many of you are familiar with MT soundings? Not a lot. Not a lot. Okay. So. Okay. Here is the Earth. Here is the ionosphere. Above the Earth, an electrically conductive medium, and one through which, for whatever reasons, currents flow. These currents generate a magnetic field, which is fairly easily measured on the surface of the Earth. These currents are present at all frequencies. Using what we learned today from Alex, we can ignore, of course, radiation effects. That means that we have a source of alternating magnetic field on the surface of the Earth, which also covers a wide range of frequencies. Associated with induction in the Earth, as discussed again by Alex, there is an electric field component, which I call the primary electric field. You may get some comment from Alex on that, because it is a derived quantity from the time-varying magnetic field. But what this means, in essence, is using these ionospheric sources, we have two very useful field components, again at right angles, a horizontal magnetic field and a horizontal electric field. We can regard this as a plane wave going down into the Earth. Again, I won't spend a lot of time dealing with the details of it, but what this means is that if we have a layered Earth, row 1, row 2, etc., by making measurements on the surface of the ratio of the electric field to the magnetic field, we can learn a good deal about the layering in the ground. Okay? So again, the ionospheric currents give us for absolutely free the primary magnetic fields, usually at strengths that are reasonably easy to measure, if you're willing to wait for an hour or something like that, but patience you need if you want to get down several kilometers into the ground. Again, induction in the ground causes a primary electric field, and we can show that the ratio of those two field components is a reasonably sensitive measurer of the geoelectric section. That is how the resistivity varies with depth. We're going to have a little problem with these lectures, because sometimes I'm going to get ahead of Alex, and so you'll have to wait for him to come along and to catch up. So that's all I'm going to say about the technique. I'm going to have trouble perhaps explaining to you adequately what I want to tell you. I'll go ahead and try, and we may have to do it again if you're interested. Again, we measure the ratio of the electric to the primary field as a function of frequency. It's just as if we had the big source in the sky with variable frequency, and we get the geoelectric section with depth. Okay, my interest today is how does the presence of near-surface conductors, indeed right on the surface conductors, affect our geoelectric sounding. Okay? Again, you'll recall that to make the sounding, we measured those two field components, magnetic field, which I've shown up here, and the electric field, which I've shown there as a function of frequency. Another quick word as to how soundings work. Again, skin depth concepts applied. You remember that the skin depth was a function of the frequency and the resistivity or conductivity of the ground. Let's suppose that we fix for the time being the resistivity at whatever value, 100 ohm meters, and we go to very high frequencies. The skin depth, a simple expression for it, in meters is 500 times the square root of the resistivity of the ground divided by the frequency. Resistivity in ohm meters, frequency in hertz. Okay, that simple expression shows that if we fix the resistivity of the ground and we find the components at very high frequencies, that our skin depth will be small. Typically, for example, if we were using a resistivity of 100 ohm meters, and if we had a frequency component at 100 kilohertz, which is very high, we would have 100 divided by 100 times 10 to the third. The root of 10 to the third is about 30. 500 over 30 is about 15 meters, something of that sort. If, on the other hand, the frequency is very low, suppose again we have 100 ohm meters, but now we have a frequency of 1 hertz, then our skin depth is 500 times the root of 100, or 5,000 meters. So that at low frequencies the skin depth is enormous, at high frequencies it's very shallow. So by picking the different spectral components, we can think of the electric and magnetic fields as being at all frequencies, and by putting in filters to select the frequencies that we want, we can vary the skin depth. By choosing progressively lower frequencies, we go down deeper and deeper, and thus we do our geoelectric sounding. So in anticipation of that, I've shown you a 3-layered Earth with the upper layer 600 meters, the next one 1,400 meters, and the next one 1,000 meters. However, I've also put this small conductive slab on the surface of the ground, and its dimensions are 40 by 40 meters, pretty small compared to these numbers, and it's only 4 meters thick. So it's tiny in comparison with these measurements. It turns out that, incidentally, in plane wave EM, everything depends on skin depth. If you want to know what happens, calculate the skin depth, and you can start making shrewd guesses as to what's going on. In this case, the skin depth in this 5 ohm meter slab is very large, much larger at any of these frequencies than the dimensions of the little slab itself. Okay, we said that in order to do the sounding, we took the measurement of E over H as a function of frequency. But what happens if we measure the electric field right over this little slab? We don't know it's there, of course. It's down 10 centimeters under the ground, so we don't know it's there. But we know that the electric field is going to be in error, and therefore our sounding is going to be in error. Because the dimensions of this slab are very small compared to a skin depth, the influence of the slab itself is not going to be a function of frequency. And the presence of the slab is going to lead to the so-called dreaded static effect. And static effect is a really serious problem with MT and AMT soundings. Right hands, how many of you have heard of static effect? Okay. Well, you're going to learn something about it for the rest of you, okay? Okay, next slide. We define an apparent resistivity from this ratio. And the definition of the apparent resistivity is such that if this ground was homogeneous, in other words, if it was all of resistivity rho 1, no layering, then our definition is such that if we measure the ratio of E over H correctly, i.e. not near any small superficial patches of the kind that we know is lurking under the ground in this case, we would actually get the correct apparent resistivity. So if, for example, the Earth is 100 ohm meters all the way down, the definition of apparent resistivity is such that if we measure this ratio and crank in the numbers out, comes 100 ohm meters. Okay, remember that we're going to make measurements of the electric field at various distances from the center of this slab. When we make the measurement way out here, we expect to see little or no effect from the slab, so we're going to get the correct apparent resistivity. As we start moving in closer and closer to the center of the slab, we're going to show that the electric field will be decreased, if this is a conductive slab, from the real value, and from that ratio, our apparent resistivities are going to be too low. Why, again, was that? Well, this is the same slide you saw earlier. Again, we're looking down on our little plate, and we went through the arguments which told us that because of the induced charges on the ends of the plate in the electric field, that the electric field in the center of the plate is less than the value outside. You remember the induced charges at the end of the plate, secondary field in opposition to the primary field, the net field, therefore, inside being less than the value outside. So if we make measurements across the plate like this, once we're truly away from the little plate, our electric field will be the external value, but as we get closer and closer to the center, the electric field is going to fall to too low an amount. That simply shows the same thing. Here's the external electric field out here. Here is our survey line going across the little plate. Way out here, the electric field is the correct value, but because of the presence of these induced charges, the electric field in the center of the slab is too low. And thus, so will our apparent resistivities. Okay, just a repetition. If the dimensions of the inhomogeneity are less than a skin depth, at the highest frequency, the electric field distortion is going to be independent of frequency. Okay. This top figure bears some consideration, because what I do here is to show the pseudo-section which is obtained when we do an MT sounding. And what I plot is the apparent resistivity derived from that ratio of E over H as a function of frequency. And frequency increases in this direction. This is the very low frequency, 0.001 hertz, up to a relatively high frequency, 100 hertz. And I show a whole suite of curves here, but initially I would like to focus our attention on the measurement stations. You remember one of those measurement stations was way off the slab. That's the top curve here, and that shows the undisturbed apparent resistivity curve as a function of frequency, or our magnetotelluric sounding. Okay, the point here is that at very high frequencies, 100 hertz, the skin depth was fairly shallow. Remember, the higher the frequency for a given resistivity, the smaller the skin depth. So at the high frequency, we would expect to see an apparent resistivity which accurately showed the resistivity of the upper layer. At the very low frequency of 0.001 hertz, the skin depth is very large. So we would expect the measurement to generally ignore these two upper layers and to show us mostly information about the lowest layer, in this case row 3. At intermediate frequencies, if we're lucky and if the layers are all fairly thick, we'll learn something about the intermediate frequency, the intermediate layer, row 2. Well, let's see if that's true. At the highest frequency, 100 hertz, we get an apparent resistivity of 100 ohm meters. At the lowest frequency, we're up close to 1,000 ohm meters. And at the intermediate frequency, we're at apparent resistivity of about 30 or 40 ohm meters. Let's go back to our geoelectric section and see if that's the case. Okay, there's our geoelectric section. Do you remember from our sounding curve at the highest frequency, we got an apparent resistivity of about 100 ohm meters? Well, bingo, we're right on there. At the lowest frequency over here, 0.001 hertz, we got an apparent resistivity of about 800 ohm meters. And we see that the basement resistivity is about 1,000 ohm meters, so we're doing not too badly. And it's a good illustration of how the technique works. At the intermediate frequencies, we got a minimum resistivity of about 30 or 40 ohm meters, and we see that the real resistivity of the intermediate layer is 10 ohm meters, not as low as the apparent resistivity showed, but definitely in the right direction. Okay, so we're starting to believe at least that the MT technique works, that we can perform a geoelectric sounding by making measurements over a broad spectrum of frequencies. There are incidentally well-known techniques which let us take that sounding curve which I showed you and convert it back into a geoelectric section such as this, subject to certain errors. Okay, that's a very, very fast treatment of MT sounding. I'm going to discuss what can go wrong with it. Does it make some sort of sense so far? Understand reasonably well. It's a widely used technique. Again, we simply measure the ratio of the two field components as a function of frequency. The ionosphere gives us the fields for free. We can use filters to select out the spectral components that we want. We plot our data out as apparent resistivity as a function of frequency, or the square root of frequency, and we get a geoelectric sounding because the skin depth varies with frequency. The high frequency measurements give us near surface information. The low frequencies give us the basement information, intermediate frequencies, intermediate depths. Okay? But I pointed out to you that one of the problems is that if we put a near surface inhomogeneity, a small conductor, for example, on the surface, that it makes a mess of our measurements of the electric field. And we now ask ourselves, okay, what does it do? And we know already, because we looked at the physics of this bit, that over the plate the electric field is too low. Right over the center, but it will be way too low. And so, since the apparent resistivity is the square of E over H squared, since the apparent resistivity is defined in terms of the ratio, Alex, what am I doing? E over H squared, thank you. We know that if the electric field is too low, at any point that our apparent resistivities are going to be too low. We know that the electric field is going to be too low here. Let's go and see what happens. Okay? Again, we look at these curves. I showed you the one at the top where the measurement was taken off the slab. There was no problem. Successive measurements here are taken at positions increasingly close to the top of that slab. Here's the slab. We make the measurement closer and closer. And finally, this measurement here is right smack dab top center of the slab. Okay, what's the problem? Well, the problem's a big one, because this curve, which is the correct curve, because of the reduction in electric field, which is not a function of frequency, now looks like this. And the apparent resistivities, instead of going from 100 ohm meters to nearly 1,000, go from 10 ohm meters, very roughly, to less than 100. That's a hell of an error. And so that tiny little patch of conductive material has really got in the way. If we inverted this data to get a geoelectric sounding, as we did earlier with this curve, we would be almost an order of magnitude low with all of our resistivities. That is a very serious error. That is astrophysical accuracy. That is not geophysical accuracy, okay? Okay, but there's something worse that happens as well. Apart from the fact that you get the wrong layering and the wrong resistivities, you also get an anomaly when you plot the data out in what we call a pseudo-section. I called that a pseudo-section. That was wrong. That's a sounding. This is the pseudo-section. What's a pseudo-section? Well, it's a plot of the apparent resistivity, or more accurately, contours of the apparent resistivity as a function of distance along the ground, done as we let the frequency decrease. So again, here's our slab on the ground. You remember that we measured the electric field at various stations, including one right on top of the slab, and here are the stations here. Out here, we agreed that we were far enough from this slab so that it wasn't affecting us, so we should get the pseudo-section that is correct for that layered earth. And so at the high frequencies out here, a large distance away from the slab, we get an apparent resistivity of 100 ohm meters. As the frequency drops, we get an apparent resistivity which falls down to a minimum of about 30 ohm meters. And then as we go further down in frequency, the apparent resistivity increases, and thus so do our contours of apparent resistivity. So as long as we're out here, away from the slab, when we look at these contours, 100, 50, 20, 20, 50, 100, 200, 500, they look rather like our actual layering did. The difference is this isn't depth, it's frequency, but we know that frequency and depth are related because of the skin depth. So when we look out here at the data, we actually see the layering that very roughly was present in the actual Earth when we made the measurement. Once we get over the anomaly, though, instead of being on this, the correct curve, we're on this, very decidedly, the incorrect curve. And what happens now is that our pseudo-section has been distorted. And the nice layering, which we saw over here, suddenly is altered. And lo and behold, what do we get? Not layering at all, but we look like we have a 2 ohm meter anomaly, in this case a spherical anomaly, with a sort of a vertical plate surrounding it. And it's at quite a large depth, if we were to believe this, because it's happening at a frequency of 1 hertz. And if we work out the skin depth considerations, 1 hertz is a reasonably large depth, typically hundreds of meters for the resistivities that I have here. And the other problem is that this looks like a very small anomaly. On this scale here, 0 meters, 50 meters out to there. This anomaly looks like it would be about 30 meters lateral extent and down of the order of hundreds of meters. Well, if we were naive about all this, we'd say very, very good. We now have a technique which lets us look for very small anomalies at fairly great depths. And of course, that's one of our exploration objectives. If we could do that, we'd be off to the races. If we could find 30 or 40 meter targets at depth of hundreds of meters, we'd be very happy indeed. And a lot of people, having looked at this data, decide just that. They don't understand the static effect, the full nature of the static effect. They don't understand that small surface inhomogeneities can cause this effect, and they think they're actually looking at conductive targets. Okay? The results depend on the nature of the layering. I still got that little slab sitting on top of the ground, but now instead of having a 3-layered earth, I have a 2-layered earth, 100 ohm meters, a relatively conductive near-surface material sitting on top of 1,000 ohm meters. If I do those calculations again, I find that here is my correct sounding curve. Again, here is frequency. High frequencies showing 100 ohm meters, low frequencies showing 1,000 ohm meters. So once I'm away from that pesky little slab, my sounding curve is correct. If I inverted that data, I'd get back reasonably closely to this. But if I'm sitting on my little conductive patch again, this whole curve is shifted down an order of magnitude. The shape of the curve is different because the layering is different. Let's see what it does to the pseudo-section. Here's our new pseudo-section. Again, here's distance away from the plate, frequency in this direction, contours of apparent resistivity with frequency, looking good when we're away from the anomaly. Remember, the ground was 100 ohm meters near surface, 1,000 ohm meters at depth. But when I get over the plate, great distortion of the curves. And now the innocent MT interpreter would say, hey, this is great. I've got a huge, great vertical conductor. Its extent goes down to frequencies much less than 1 hertz, down to 100th of a hertz. This thing must go down forever. And it's also fairly narrow in this direction. So goody, 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 I've got a technique which lets me detect conductive dikes of enormous depth extent, very narrow ones. Boy, do we have it. But the problem is, as we've seen, that these distortions are brought about solely by that little plate sitting in the center. Okay, I think that you probably got the point. I'll whip through some of these slides. Basically, I just simply changed the layering. Now a conductor in the basement and a resistor on top. The nature of these curves changes to reflect the different layering. And now we see that our apparent anomaly caused by this little plate now looks like a conductive dike coming up from great depths to near the surface. And again, we would make great claims both for its depth, that is our depth of exploration, and our ability to detect thin targets, both of which would be erroneous. The effect of the orientation is important. In the case where you have I dealt before with a square, if we have a long, thin target, For the reasons which I discussed earlier, the electric field inside is roughly the same as outside. So at least insofar as electric field measurements are concerned, the error is not too serious. That's only part of the story, but we'll stick with that for the time being. If the slab looks like this, with a large extent perpendicular to the electric field, the internal electric field is very low compared to the outside one, and the error is very large. So it depends on the orientation of your inhomogeneities with respect to the electric field. Okay, that's simply a summary. I've done some further calculations, and the reason I'm showing you these calculations, I don't care what you do, except I want you to remember what the following set of pictures looks like, okay? Because as sure as God made green apples, you're going to see some CSAMT data, and I want you to look at these pictures and say, I know I've seen this before, okay? And I remember that McNeil said, watch out for near surface anomalies, because people make very extravagant claims for CSAMT and AMT surveys in terms of their ability to detect small targets at great depths. It ain't so. How do we know it ain't so? Because we can do the forward solutions for these small targets at great depths, and you're not going to get data that looks like I'm about to show you. So in this case, I've done very, very simple approximate calculations for a sphere situated not very far underneath the surface of the ground, 2 meters, and I'm going to let the sphere, I'll let this depth vary a bit, and I'm going to do some calculations with a sphere of radius 2-3 meters, okay? And let's look what happens. In other words, initially I had a square on the surface. You know, at least if you're smart, you could look down and say, hey, there's a conductive square on the surface. But now I've buried my little sphere underneath, a couple of meters, so you can't see it. Okay, so again, here's the pseudo-section. There's my little sphere crouched down there giving us trouble. Depth of 3 meters, radius 2 meters. And I've done a MT sounding. Here's my frequency. Here's the popular pseudo-section. And over here we see vertical contours, and they're caused by the errors in the electric field measurement right over the top of that little sphere. Note that these vertical contours go right down to the lowest frequency, and they are conductivity lows or resistivity, conductivity highs or resistivity lows. That little sphere there looks like a very deep dike going down to great depth extent, and the sphere is tiny. If I bury the sphere a little bit deeper, 4 meters, and make it a little bit wider, a little bit larger, the contours smear out. So now if you were carrying out the interpretation, you'd say, hey, great, a fairly deep conductive zone there, and yet it's being caused by the dinky little sphere. If I let the ground be layered, up till now you hadn't noticed, I didn't bring it to your attention, it was 100 ohm meters. Now I've got 50 meters of 50 ohm meters and a resistive basement. Remember this picture. You're going to see it again, okay? In the next 5 years, someone's going to show you something like that. And he or she is going to say, hey, those contours on this pseudo-section look like I've got a conductive trough, okay? And I want you to say bullshit. Okay, and someone else is going to say, hey, look at this, I've got a conductive dike coming up from depth, okay? And what I did here was I just changed the layering of the earth. Remember what you're supposed to say. Okay, and I did a third one here. Now I have the earth layered, 3-layered earth, resistor, conductor, resistor. You're absolutely guaranteed to see that one. Don't forget the magic word, that's a big conductive dike. of limited depth, extent, and not coming up to the surface. And again, I change the layering, and these effects are strongly dependent on the layering. That's the point. As you can see, now I've got the famous dog legs. That's one word for them. Anyway, you'll see that one a lot as well. So if you look at CSAMT data, and I will show you some, you're going to see a lot of that sort of effect. Okay, CSAMT, AMT, MT, small conductive sphere buried at a depth of 3 meters gives you a response that closely resembles real CSAMT data, and I'll show you that is often interpreted in terms of targets at great depth because of low frequency response. Okay, this is probably the world's worst example of a CSAMT survey. It's in the open literature, so it's fair game. It was done by Zong as a demonstration for Ben Sternberg at the University of Arizona. Here you guys is what CSAMT looks like. Okay, how do you do CSAMT? Well, CSAMT is control source AMT. We're going to measure E and H, but instead of relying on the currents from the ionosphere, we're going to set up our own transmitter. And here is our transmitter. It's 1,000 meters long. That's a long transmitter. It's carrying 4 amps, so it's reasonably heavy wire, and it's grounded at both ends. And when we look at the theoretical magnetic and electric fields from that type of transmitter at large distances from it, we expect to find an electric field in this direction and a magnetic field in this direction, as long as we're many skin depths away from the transmitter. And this looks like an ideal way to do soundings, because out here we only have to measure a coil, we only have to move rather, a coil and a small electric field antenna to do our soundings. And in theory, by making those measurements of crossed E and H, we can do soundings down to depths of thousands of meters using tiny equipment. So in principle, it sounds very attractive. Now, in this case, the survey site was 2,000 meters away from this long line. The survey line itself was very, very short. It turns out it was only 20 meters long. And the electric dipole which was used, that is a little grounded electrode array, to make the measurements was itself only 2 meters long. So way over there is the transmitter. We're going to do a profile 20 meters long, and we've got a little electric dipole which we're moving across the Earth. We also have a coil to make the measurement. So we're measuring crossed E and H. The source goes from 10,000 to 10 hertz, so we should go down to relatively large depths. These are the sounding curves cast as apparent resistivity as a function of frequency. And what you see that we get at each of these stations is essentially the same type of sounding curve, but that as we go 2 meters, the curves are lifted up or down by a large amount. Again, these stations are only 2 meters apart. Why? There's patchy, this is out in the desert in Arizona, lots of soil salinity, lots of patchy conductivity on the top, and lots of error in our electric field measurements. So clearly we have a 3-layer case there, or something which is close to a 3-layered case. But the trouble is we don't know which of those curves is the right one. And there's an order of magnitude in the apparent resistivity. So our odds of actually getting the correct geoelectric section are not too good. But let's look at what happens when we take this data and throw it into a pseudo-section. Again, the Earth is layered, no doubt about that. Essentially 3-layered, conductive at the surface, a resistive intermediate layer, and then a very conductive layer at depth. No doubt about it. And since these curves are all the same, essentially, there are in reality no lateral changes of resistivity at depth. Okay, this just shows you what happens when you try to invert that data. I inverted the data at 3 stations, and here are my 3 geoelectric soundings. And you can see that they're very, very different. In the 3 cases, my intermediate layer varies from 80 meters to 212. The resistivity varies from 108 ohm meters to 18 ohm meters. Static effect is a very serious problem. We don't know which of those is correct, and we really don't. You know, I showed you all those curves. Your guess is as good as mine as to which is the correct one. But then I put the data in pseudo-section form to complete my GLE, and there's what it looks like. And you remember I told you to remember the pictures of the dog's legs and the egg, and you can see that they're all there. There's the dog leg, there's the egg, another egg over there. What should this data look like? It should consist of a series of parallel horizontal lines showing the true layering. That's what it shows, and you see that all these effects are at a relatively low or intermediate frequency, so the uninitiated would think that they were occurring at fairly substantial depths. And they would say, here's a vertical conductive plate, fairly thin, etc., etc. It's not true. It's not there. Yeah.
See on the central left there where you're starting to approach horizontal lines.
Yep.
Would that be approaching the correct solution?
Well, it's certainly approaching a layered Earth solution, okay? As to whether it's approaching the correct one, we could flip for a bottle of beer on that one, okay? We don't know. Probably. It's certainly probably getting closer. Are there any other questions? You know, you're unwillingly learning something about something that you may not want to learn, but as I say, I absolutely promise you within the next 5 years, you're going to see some of this data, and I want you to remember this golden moment. Okay, just for the hell of it, I play a little game with the data. I bury some gold in the ground, and I don't bury a small amount of gold. I bury a sphere of gold 4 meters in diameter, not a bad target, worth $10 billion US a few years ago. I don't bury it very deep. It's down 2 meters, okay? So if you kick hard, you might tell it's there. And I superimpose the response on that on my CSAMT pseudo-section. This is not very fair, but it's what could happen. Okay, well, the question is, where's the gold? You don't remember exactly the last one, but you remember it looked pretty well like that, eh? Well, the gold is over here. It's at 3 north, okay? Where's the gold over here? Jesus, I thought it was there. I'm not so sure now. It's over here, okay? Huh? There it is. That damn gold keeps moving all over the place. I'm telling you, if it wasn't for the triangle, you wouldn't tell where the gold was. Okay, well, that goes to show that, as Alex will discuss later, that the influence of geological noise is very high in plane wave systems. The static effect is very, very serious one, and it's a very poor way of looking for massive gold or massive sulfides. Just for the hell of it, I show you the response, and this is a rotten slide, from either our EM31 or our EM38, and these are little inductive EM systems. This one has an intercoil spacing of 4 meters. One guy or one girl can easily carry it. This one has an intercoil spacing of 1 meter, and these profiles show the anomaly as you go over the gold with either instrument. Either instrument would show a slowly varying component because of the conductivity in the ground, because it's varying, but they would show a large and well-defined target over the $10 billion of gold. and you'd be home for a beer with a happy look on your face. Okay, so galvanic current components make a big mess of AMT and CSAMT. There are supposed to be techniques, now this is a really biased remark, there are supposed to be techniques which help get rid of it. I have yet to see CSAMT data or AMT data. Usually shallow sounding is bad because the electric dipoles are small, which I really feel was adequately treated and that I would trust for exploration purposes. Okay, let's take how about we just take a break for a few minutes? It's 5 o'clock. Peter, what do we want to do? I have about another 20 minutes. Do you want to count it and go home and play volleyball? Or do you want to continue? I leave it up to you.
It's about another 10 minutes, 15 minutes before the people who are going to be supervising volleyball come, so we can go.
Bad luck, as it were.
Big feature.
Really, really, really good point, okay? I don't have any. But what people should do, and I cannot understand why they don't do it, I was just discussing this with Peter, when you interpret a CSAMT section like that, go and do the forward model. It's easy. Most of us now have the programs, you guys certainly do, where you can do that, do the forward model, throw it into a pseudo-section, and see if it looks at all like what your field data looked like. My suspicion is that in 9 cases out of 10, it won't. But it's an awfully good check, and if it does look the same, then I'm a liar, okay? And you've got yourself a good measurement. Did you have a comment, Alex?
I would like to emphasize what you told. First of all, two problems.
Mm-hmm.
One problem, near surface, we have inhomogeneities, very often completely near surface.
Mm-hmm.
They affect on behavior of the fields which we measure without them. Now, their influence remains in all frequencies, at all frequencies. This phenomenon was discovered, I would say, many years ago. There is magnetotelluric soundings. It was time when all oil companies used this method. A lot of forward modeling was performed. Nobody cared about pseudo-section. Pseudo-section is an invention which does not have any relation to whether there are inhomogeneities or not. But pseudo means unreal. Somebody, I don't know who, but I came not very young geophysicist from good classical school of geophysics. And I discovered there are geophysicists who invented this pseudo-section. It's not established, it's not proved, it's imagination, it's a fiction. So, if for those who don't know pseudo-section, simply perform magnetotelluric soundings, they quickly discover, those who did it, that apparent resistivity curves distorted, and in a very small distance from each other. Point observation one place, then 1 kilometer, completely another curves. Apparent resistivity curves is a classical approach, and it was established distortion. Therefore, it was dangerous to interpret. That's the reason that no more magnetotelluric sounding, neither west nor east, for oil exploration, except maybe 2, 3, 4 cases in remote places, far away, where it's new areas where nothing can be done. So that's the fact that there is influence of upper inhomogeneities is extremely well established. Perform forward model. It's proved that in magnetotelluric, it's proved that presence of upper lateral change of resistivity above creates fictitious layers which don't exist. So, additional to it, somebody invented with these pseudo-sections, and which is this pure emotional approach to interpretation. And I would understand it's a very, very strange situation. It doesn't mean that control source MT or magnetotelluric cannot be used if there is no lateral change of resistivity. It's a normal geophysical method. But as soon as there are lateral changes, it's proved, performed forward modeling, everything is done, and it's this interpretation of such methods creates fictitious anomalies. It's known, it's not subject of research, it's no known fact, and that's what I would like to share with you.
Okay, just to continue on, you know, the problem, of course, is you have near surface conductive inhomogeneities, and you don't know they're there. If you know they're there, the problem gets a lot easier. And one of the approaches, particularly with MT, which has been used reasonably successfully, is to use time domain EM to learn about the near surface resistivity characteristics. And one of the advantages, as Alex will tell you, is that TDEM is a technique which has a relatively narrow regional influence. In other words, you make a sounding here, and that's where you're getting your data. It's not from way over there or way over there. So what they do is they make TDEM soundings, they convert the data to apparent resistivity, they then, a geoelectric section, they then take that geoelectric section and they calculate what the AMT response would be, and lo and behold, in a large number of cases, what they get is something that looks like this. Again, here's your 1 over frequency. Here's your apparent resistivity. And here are your MT soundings. You know, all your soundings looking the same but displaced by an unknown amount because of surface inhomogeneities. And then they get their TDEM sounding, they convert it to a geoelectric section, they calculate the MT sounding that they would get, and lo and behold, it might look like that. And so that immediately tells you that this is the right curve and you're off to the races. That works well in the cases, and there's a couple of papers in geophysics, one by Ben Sternberg, which shows the successful cases, so I'll promote it. But at any rate, as long as the lateral variations are not so bad that they're also distorting the TDEM survey soundings, and that of course can happen, the technique looks like it works really fairly well. Okay, we're going to race ahead with large loop sounding and measurements, ore body exploration. I lay out a large loop on the ground. I energize it either sinusoidally in the frequency domain or in time domain with an alternating square wave, doesn't matter. And of course, down here, for the sake of argument, we have a primary magnetic field from this loop. Everybody knows that. But also associated with the time-varying primary magnetic field, we have an electric field in the ground, which looks like that schematically, and of course, which is what causes current to flow in the ground, assumed to have finite conductivity. So if I've got a target down here, it's going to have a magnetic field component and an electric field. And as we know, that makes it a candidate for galvanic current component. And I'll tell you, that's no news to anybody that does surveys in Western Australia. So again, I schematically show my plate down here. I show the this is kind of a messy slide, but I assume the magnetic field down there causing vortex current flow in my target. I now know that I have a significant electric field component, and as a result of current gathering, I get also an anomaly from the target. Again, both of them, if I measure the vertical magnetic field, not the horizontal as suggested here, will give me a similar response. The shape of the vertical magnetic field or the horizontal magnetic field isn't going to help me in deciding whether I have vortex or galvanic current flow. Okay, we did a large number of calculations. I told you that all my slides are in your handouts. This is a paper in Geophysics of about 10 years ago. Basically, we did approximate numerical calculations of the response of a large plate-like target in the time domain to a large loop. Peter, I suggest that maybe we should stop now, okay? Because otherwise you're not going to get much out of the next 15 minutes. And besides, people are starting to do this, sitting in their seats. Okay? Good. Yeah. Okay, good. Thanks.